Aloha, Richard Halverson here. This is ITS148, and today is March 24th. And see, let me share my screen. So it's screen number 2. And let's see, I was just getting going here. Let me go to Lima. All right, so we are down here. So sorting. Did I talk about? I don't know. I can't remember if I talked about searching. Did I talk? I can't. I better check. I don't want to skip searching because that's. I was going to talk about sorting today, but let's see how far I got last time. I didn't talk about searching. Okay, well, let me talk about searching then first. I better do that because we talk about analysis of algorithms. And analysis of algorithms is like a real important part of this course. Okay, so searching algorithms. There's two kinds of two common functions that we need to do when we're dealing with lists is to sort them and then to search for an element in the list. And so first we're going to talk about searching, and searching is a good thing to start talking about because we also have to learn about analysis of algorithms. And what that is comparing, you have two algorithms that do the same thing, but one can be one's going to be faster than the other, most likely, but also when the size of the list grows, how does that affect the time that the algorithm takes to execute? And so let's see. Let me just do a simple thing here. I'm gonna move to a different part of the. I'm gonna move to a different part of the ship here because it's kind of distracting. All right. So first we start out by comparing linear search and binary search. So let's say you're searching for key number. Let's just run this and see, and I can explain as we go. So let's say we are searching for key number 14. We step down starting from the beginning. There's no way for us to really glance at the whole thing and say, oh, it's number 3. We have to start at the beginning and search down. And let's say we're searching for 11. It looks at everyone, and we don't find out that we don't have an 11 in the list until the very end. Okay, so the worst case time for this algorithm, depending on the number of elements in the list, is the number of elements in the list. Okay, so and so this is the algorithm for a linear search. Here we're just loading up a list. We have a list here, and then it asks us what value to search for, and it calls this linear search algorithm, and this thing loops starting from the 0th index all the way up to the top of the list, and it just checks to see if the number is equal to the key that we're looking for. If it is, we found it, so we return the index. We're looking for the index. Otherwise, we return a -1, and that indicates that the element is not in the list. So make sure you understand linear search. Very simple. The runtime here. Here's where we're talking about where the amount of time that it takes is proportional to the number of elements in the list. For a list with n elements, the linear search thus requires at most n comparisons. The algorithm is said to require on the order of n comparisons. So it's the, and you write it O parentheses n, O of n, the order of n, on the order of n. Okay, so you can answer these questions as multiplying the number of elements times the comparison, how much time it takes and so on. So now we're going to look at binary search. And with binary search, we have to start with a sorted list. Okay, that's the requirement for that's the expense. If you have this big long list and it's not sorted, then binary search won't work. But binary search, you'll see, is like way faster than linear search on average. And so it might very well be worth it to sort the list first. It's not always worth it because sorting is a very expensive thing to do also time-wise. When the list is really long, it takes a really long time to sort. All right, so the way binary search works is you're looking, okay, the list is sorted, so you start by, so you have a key value that you're looking for. Let's say you're looking for one of these names here. You start by looking right in the middle, and you look and see what the name is, what the key value is for the element that's right in the middle. So you take the index, if it's got 100 items, 100 in there's 100 items in the list, they're all sorted. So you start with number 50, and you look to see what number 50 is. And if the key value that you're looking for is less than the key at 50, then it's going to be in the bottom half of the list. If the key value you're looking for is bigger than the key value at index 50, then you know that what the key that you're looking for is in the upper half of the list. So right away with one comparison, it's also possible that the key value number 50 is actually the key value you're looking for. And if that's the case, you found it already. But the idea here is with binary searches, with that one comparison, you've eliminated half. Okay, so now we aren't looking, let's say it's 1,000. Now we're not looking at a list of 1,000 anymore. We're looking at a list of 500. It's either going to be the lower 500 or the upper 500. Okay, now we keep on doing that same concept, looking at the middle one. It's either that one, or it's the lower half or the upper half. And so each time we cut the list that we're looking for, the item that we're looking for, we cut the list that we have to look in half, and we're either going to find it or not. But by cutting the list in half each time, for example, for a list of 1,000, cutting the list in half each time, that means cutting the list 10 times, it's at most 10. Because each time you cut the list and it turns out that 2 to the 10th power is 1,000, so that's where we get the 2, and that's where the exponent and the log come into play, and so that's how we will analyze binary search. Okay, so that's how binary search works. You can go through and go through this. Let's see what example they use. So here we've got. We're searching for Pooja, and it starts with the middle one, and the middle one turns out is Muhammad. So it's going to be in the upper half. So we've eliminated the bottom half. So we're looking in the upper half now, and we split that in two. And the middle one is Sherrod, and it's between Sherrod and Nigel. It's in this Sherrod. Split this one into two, and now it's. This is a quarter of the list, and we keep on going here until we find it. And as we're searching, we have these indexes that keep track of the bottom of the list and the top of the list that we're looking at. Okay, and each time it gets cut in half, and as we're going, we either lower the upper index, or we let's say, let's just get this picture right. This is lower and this is upper. We either lower the upper index down to here, or we raise the upper index up to here. Each time it gets cut in half. And if these two should cross, then we know that the element is not in the list. And that's how the algorithm works. So here, this cutting in half, this makes sure you understand how that works. What is the first context searched? 0, okay, so 1, 2, 3, 4, 5, 6, 7. 7 elements in the list. So the middle one would be Holly. I believe it's Holly. Let's see. Yes, it's Holly. All right, so so this shows how binary search works with numbers. And so you can click through this. You're gonna have to click through this so you get the points. See, high and low are these two indexes, and the first time it computes what the middle is, and so that's the middle. And we're looking for 16. Is the middle one equal to 16? No, it's not. It looks like it's in the upper half. So now we raise the lower index to here. The higher index we leave the same. We compute the middle. Is it that one? No, it's not. So it's in the lower half. So now we figure out what that is, and it turns out the one we look at is 16. So we found it. So that's finding it. Okay, so here's the algorithm, and this is a iterative version of the algorithm. Are we going to talk about a recursive version, I wonder? Because this binary search lends itself very well to a recursive algorithm, because you know, binary search, you know, just, you know, calls itself, looks at the middle one. Is it the middle one? No, it's not. Is it in the lower half? Let's say it's checks to see if it's in the lower half or the upper half, and whichever half it's in, it calls binary search on that half. So it keeps on calling binary search until the indexes cross or until you actually find it. And so, but this is an iterative version where we actually have these indexes here and we're moving them back and forth. We're actually moving them back and forth that way. So this is the algorithm. Make sure you understand how that works. And here it talks about efficiency. Okay, so here's where we talk about efficiency. You should read through this and get all the points. It's basically telling you that each time you do a comparison, with each comparison, you either find the element or you cut the search list for the next comparison in half. And so if you keep on cutting it in half, you get down to 0 or 1 very quickly. You know, 1,000, if you cut 1,000 in half, it's 500, 250, 125, you know, 62, you know, 31. So 10 of them, you get all the way down to 0. All right, so so that explains the differences between, and so here now we introduce us to this O notation, and this is a really important thing to know how to do in computer science. So it's whether whether you get a computer science programming degree at KCC after 2 years, or you go on and get a bachelor's degree in computer science or computer technology or information technology with programming at a 4-year, you have to understand O notation and figure it out. It's actually really easy to figure it out because it's all a bunch of estimates. It's tricks to see it. You see what the biggest one with the biggest exponent is, and that's what it is. You can ignore anything smaller. And if you do something like study computer science, like more at the graduate level, that's where you figure out better algorithms. And what's a better algorithm? It's an algorithm with a better O factor. many PhD theses. You know, we didn't start really studying computer science algorithms until the 70s, and all of the outstanding, you know, discoveries in algorithms have happened since then. So it's kind of interesting because when I started learning computer science back in the 70s, you know, the fastest sorting algorithm was going to be, you know, O of n log n, but the trouble with O of n log n is that there's no stable sorting algorithm that's O of n log n. So if you wanted a stable sorting algorithm, you had to do something less than O of n log n. You had to go to an O of n squared, which is bigger than O of n log n. But since then, someone has discovered a fast, and we're going to talk about sorting algorithms and fast sorting algorithms. These are okay. The sorting algorithms, when we get there, are these are all O of n squared. You know, n to the 2 power is bigger. You know, n times n is bigger, which is n to the 2 power, which is n squared. N times n is bigger than n times the log of n. You know, the log of n is it's in between n and 1. But these sorting algorithms here are all n times n, and these sorting algorithms here are n times log n. And so we will study both of them. And in this, and we're gonna run a program. Your next assignment is going to have. I'm going to take you through setting up where you can compare the performance of these algorithms. I did this as an example in my 228 class, and where I created it, you know, in class just to show them the difference between these sorts that we're going to learn. So I'm going to have you create this program right here. You're going to have all the sort programs, and you're just going to put it together. But doing this and running this, it'll really bring home the difference in these sorting algorithms. So this is sort of what your final program is going to look like for sorting. I'm off on a tangent now. I'm off on sorting. That's what I planned on talking about this time. But so if we're sorting a list of 10,000 items, and so this fills an array with a random 10,000 items, and then it compares these sorts. And the selection sort takes 4 seconds. Insertion sort takes 6.6 seconds to sort 10,000 items. And then these other sorts take way less. But if you're only sorting 10 items, insertion sort, you know, is the fastest because there's overhead to set up these other ones. All right. So, but anyway, that's where the computational complexity, or the big O notation of functions, come in. Okay. So this takes you through the steps of figuring out what the big O notation is. And the first step is to count your loops, to count your nested loops. Basically it's counting the loops that depend on the size of the input. And so you can come up with some sort of equation for it if you want to. You don't need to, because there are tricks to just looking at your code and say, oh, there's an outer loop and an inner loop. Okay, oh, that's n squared. Okay, because the outer loop assumes n, the inner loop is about n, maybe just one less than n or something, and each time the inner loop takes n, but then you do that n times, because there's an outer loop which makes the inner loop execute as many times as the outer loop executes. So when we get into this, we may do a couple, but really all you need to know here is that you take the biggest term and you drop off everything else. Okay, you drop off all this other stuff, and this is going to be O of n squared, because n squared is the biggest term, and all the rest of the stuff, you know, this is the dominant term. And here we're talking about, you know, if we're going from 1,000 to 1 billion or something, it's going to be this is going to be the dominant thing. And whether it's 7 times or not, doesn't matter. You can always get a computer that's 7 times faster, but it's this this thing going increasing at an you know, n squared rate is what takes all the time. Okay, so this just takes you through this to have you recognize the what you drop off and what you don't. So which of the following big O notations is equivalent to this? Well, n changes with the size. So if n is only 100, well, yeah, that. But what if n is, you know, 10 billion? Okay, well, this is nothing. And if this goes from 10 billion to 100 billion, it's this thing that's going to dominate. This is just going to be, so it's this, I hope, the highest order term. So this is for composite functions. It's, you end up, you know, using the bigger one. Determine a simplified big O. If you've got this, I guess it's this, because you drop off all the smaller terms. Okay, here, this is an important table. This talks about the growth rate. And it's all about the size of the input. It's all about the size of the array that you're processing. And you know, there's time and there's space also. We don't talk too much about space, but with merge sort, there's a space growth also. So here, for example, and that's kind of what I was sort of showing you with the this program that I was running. If you have a log n, okay, so binary search is log n, linear search is n. Okay, so linear search is bigger because it takes longer, because n is bigger than log n. Okay, so here, this is what it looks like. We've got log n and we have n. So when n is just equal to 10, when there's only 10 elements in the list, you know, this is faster. When there's 50 elements in the list, see, this is growing exactly with n, because it's O of n. When, you know, if 10 takes 10 microseconds, then 100 is going to take 100 microseconds. 1,000 is going to take 1,000 microseconds, and so on. 100,000 is going to take 1 second. But log n doesn't grow like that. Log n grows at a much more dampened rate. And, you know, 3 to 5 to 6 to 9 to 13 to 16, you know, from 3 microseconds to when you double it, it's 6 microseconds. You double that, it's about 13 microseconds. Well, okay, so we went from 3 to 6. Well, n has gone from 10 to 100, and we go from 6 to 13, about doubling it. N has gone from 100 to 10,000. So you see the growth. That's the difference in growth. Well, n log n, these are all the sort algorithms. These are the fast sorting algorithms, and you can see, you know, n squared is n times n. So this one here, this one is n times log n. It's basically this one times this one. So this times this is going to be less than this times itself. Okay, so this one here, this row is this times itself, whereas this row is this times this. Basically, that's the way you can kind of look at this. And so when we're talking about sorting algorithms, we're talking about this row or this row, pretty much. And so, you know, sometimes it's real important to go with the faster one, because if you're doing stuff way up here, we're comparing, seconds to hours. If we're down here, it's 0.28 milliseconds to it's 0.28 milliseconds to 2.5 milliseconds. Well, a millisecond can't even tell the difference between those two. You can't, it's hard to tell the difference between a lot of these, but when you get up here, you can definitely tell the difference between 1.6 seconds and 2.7 hours. That's n squared growing. Of course, n cubed is worse. And then, there's beyond that, there's where n is the power of something. Okay, so here you're just taking n times itself, some number of times, n times n squared, n cubed, and n to the fourth power. Here it's 2 to the n power. Okay, so if n is 10, it's 0.001 seconds. If n is 50, we're talking 35.7 years. Okay, so going from 10 to 50 goes from 1 microsecond to 35 years. And it turns out that there's a class of algorithms where trees and graphs traversing a directed graph. For example, in real life, it's, let's say, traveling salesperson problem is a good example. Where, let's say, you're a traveling salesperson problem. You're a traveling salesperson, and you have to hit 5 cities. LA, Houston, whatever, Chicago, Minneapolis, whatever, 5 cities, and there's flights between them. Let's say we're doing cost, and the cost per flight, there's different costs per flight between the cities. You can go from any city to any city, just costs a certain amount. And you're a traveling salesperson. You got to hit all cities, doesn't matter what order they are, and you want to know the cheapest. What's the cheapest set of tickets to hit all the cities? And so that's a traveling salesperson problem. That's this thing. That's n squared. That's an n squared problem, and if you can. It's non-polynomial. So if the big mystery today in computer science is, can you find an algorithm whose order of magnitude is less than n squared? If it's below, less than 2 to the n, where it's not a power, where it's just a term, that's perhaps has an exponent. Okay. Right now, all of the traveling salesperson type problems are in this range, and the big mystery is, can you find one that's down in this range? Somewhere it can be 4th or 5th, whatever. And so they haven't found one, but they can't prove that they can't find one. See, so that's the big mystery. If you can either prove that they can't find one or find one, then you'd be richer beyond the dreams of Aberth, or whatever. Okay, so this is growth rate, and so you want to let's see. This class started at 10:45, right? Yes, 10:45. All right, and here this is nice. These n factorial, I guess, is worse than n is 2 to the n. N factorial is worse than 2 to the n. That's funny. Let's okay. Oops. 2 to the n and n factorial. Okay, it goes much faster. Runtime complexities for various code examples. Okay, here's some code examples. Find the minimum of x and y. Well, that's O of 1, because it doesn't. Well, that's O of 1. binary search is log n, because each time we cut it in half, this cuts it in half, where we're next gonna look at the upper half, not the lower half, and this cuts it in half if next we're gonna look at the lower half, not the upper half. And this is the linear search where the worst case, you gotta look at every one of them. Best case is it's the first one. And then this is a merge sort, which is O of n log n. And so it's interesting the way merge sort works. It does do this sort of divide and conquer thing, where it really lends itself well to recursion, as you can see, where we'll study a merge sort next time. Selection sort is just n squared. It's a nice sort algorithm, but trouble is it's x squared. It's called quadratic. And then something to the power of n is exponential. And computing the Fibonacci sequences, an example of that. So and this just helps you understand it. You know, this is a constant. There's no variable in there. And O of n. Oh, look, I guess it's log linear. This is the linear part, and this is the log part. I guess that's what it is. Interesting. So this would be n squared, so it'd be is there such thing as linear quadratic? I think it's just quadratic. All right, I'm going to say quadratic. Okay. There's no such thing as linear quadratic, I guess. A linear search has a O of n runtime complexity. It's the binary search is O of n log n, and there's no search that takes n squared, and it just takes one pass through. Selection sort is n squared. Okay, so you can do that algorithmic analysis. Here we talk about worst case and I guess average case. So here it's pretty easy to figure out. You know, you just do the worst case. You look at it, figure out the worst case. So yes, and something like for some sorting algorithms, worst case would be you want to sort the list in ascending order, and you throw at it a list that's in descending order, and it does. And if it's the type of sorting algorithm that relies on swapping as you go up as you traverse through the array or whatever, that would be how you would figure out the worst case for that. And so the trick is kind of figuring that out. Here what is the big O notation for the worst case runtime? Each time you're cutting it in half, n val is equal to n, and you loop through here, and each time you're cutting n val in half until you're done. So I would say it's this. N val decreases by half each iteration. So go through here and try to understand, you know, first figuring out what f of n is, and then O of n log n. It's just patterns, figuring out the patterns. And you aren't going to have to actually solve any of these problems. So you're being exposed to it, and you're learning it by going through these little exercises, and you get as many chances as you need. And so it's good to learn this stuff. It's good to be aware of this stuff. And sometime when perhaps you're really being asked show that your method, your function is more efficient than some other function, you would be able to go back and you would know that this is how you do it. Do a little bit of Googling, and you should be able to utilize these techniques if you need to someday. If it becomes important in your studies, you're going to see it again, and you'll actually have to do some problems in it, but you will certainly, you've been exposed to it, and you will sort of understand the big picture where it's going. Here, this thing, this is an example of how you may have to do a little bit of algebra to arrive at what the big O notation is. But so you can go through this. You should go through this. We are in a couple of labs. Oh, well, let's do a lab. All right, let's do this one. I haven't even looked at these. Given a sorted list of integers, output the middle integer. Assume the number of the integers is always odd. Why? Because it makes it easy to find the middle. Output the middle integer. Nine. All right, so you're supposed to read in an input list that looks like this and output the middle one. So I'm just going to take a guess here. Input list equals input whatever. And then I'm going to I don't need to, it's a sorted list, so I don't even really need to look at the values. I'm going to assume that I get what they tell me. And so I can just do items. I'm supposed to okay, equals input list split. And because I'm splitting in a space, I don't need to put any argument into that. You just do left, right parentheses, and then side. Okay, so the middle item is middle index equals the number of items in the list, which is len items. Divided by 2. I better do an integer divide, and then I'm supposed to output it, print items, and it's an array, so not an array, it's a list. It's a Python list, which is an array in any other language, middle index. So let me run this using something. This is 148. I'm just going to get do I have some sort of test? Here's a test.py. Do it this way. Let me get rid of this. And I'm going to take this. Take this code. Paste it there and save its test.py, then bring up my command line, which was this over here. I gotta go back to cd / ITS148 because that's where that is. And so I can do Python test.py, and it's asking me for whatever it is, and I'm going to put in this. I'm going to put in 2 space 3 space 4 space 8 space 11, and what comes out is 4. That's the right one. So this will probably work. Two space 3 space 4 space 8 space 11. You know, one thing that we really fall short on in this class is coming up with test data, coming up with data to test your code. And so I gotta we do more of that in 228, but I'm gonna have to figure out how to help you guys know how to develop good test data for your programs, because in the real world you probably won't have that available to you like you do here. All right, so here's binary search. Let's see what this one looks like. Binary search can be implemented as a recursive algorithm. Yes. Complete the recursive function with the following Are we actually supposed to write the binary search program? Oh, here we are. We're writing the binary search program. Okay, so so the program is you're reading a bunch of integers. I'm going to take this out of here. Copy this. Put it over here. Paste it there. Save it. Okay. So this asks for a list of numbers. I think it's got to be sorted, right? Doesn't say it has to be sorted, but I'm supposed to record the number of recursions. Okay, so I'm going to put something here. Enter list of numbers, just so I know what it's asking for when it's sitting there and not doing anything. And here we're asking for enter a number to search for. This converts it into an integer, and then we're going to call the binary search program on, and these are what the arguments look like. These are the numbers. This is the array, goes in there, and this is what we're looking for, and this is the range of the indexes to look in when you're looking at the nums for the target. So and then when we're done, we print all this out. Where does recursion, how are we supposed to keep track of the number of recursions? Complete the okay, list of integers, target, lower and upper bounds. That's the binary search function. Return values that's found. The algorithm begins by choosing the index midway. Okay. So I guess I gotta declare global variables up here. Recursion equals 0. and comparisons equals 0. And okay, binary search. Okay, so we have an array of in a list called nums, and we're looking for a target. So the first thing it suggests we do is I'm going to use the suggestions here that they suggest. The algorithm begins by choosing an index midway between the lower and upper bounds. Okay, so lower and upper bounds. So mid index, it's calling it index, choosing an index. Okay, so I will call it index also. Index equals the middle of lower and upper bounds. So it would be how do you figure out what the middle is? It's lower plus upper divided by 2 or something. Lower plus upper divided by 2. Try to do integer divide. I'm gonna pop this 15.6. Binary search. Yeah, mid equals 1 plus I divided by 2 like that. Okay, very good. I got that right. Okay, let me just put this back up here. Okay, that, and then what does it say? Tell me to do next. Let's go back to here, and it says to. Okay, so I've got the index, and I say if target equals nums of index, then return index. Oh, okay. Now I can actually, I don't need to do else or anything, because if that is true, it's going to return, it's going to be gone, and I don't need, it doesn't matter what's after it. So if it reaches here, if it reaches this point, then I know that the target was not equal to nums of index. So now if it reaches this point, I got to check to see if the upper and lower have crossed. No, do I do that? If upper equals lower, return lower. If upper equals lower, return lower. I see. If upper equals lower, then if target equals nums lower, then return lower. Okay, so we're done now. If it makes it to here, if this is false, then we come here, and otherwise return -1. Otherwise, if this is not the case, and if this is not the case, then we need to call. Otherwise, call the function recursively with half the list as an argument. So I do. So I got to figure out if it's the upper half or the lower half. So I do if nums. I'm looking at this right here now. I'm looking at this right now. If nums of index is less than the target, then I want to, that means the target is above nums index. So that means I got to do a binary search on the upper half. So if that's the case, then I want to do a binary search. I want to do something that looks just like this. Okay, I want to do something that looks just like this, but I think I want to return this. I think I'm returning this because this is going to return something. See, it's returning this. It's either returning this or it's returning this, or it's going to return what comes back from searching the top half. And the top half is going to be, this is going to be index +1. +1, comma, upper. See, that's the upper half. Else, actually, I don't need to do else because if it makes it all the way to here, nothing above it matched. So I can just say return. I can say the same thing, except I'm doing lower index -1. So so when it comes in here, either it comes in here, it computes the middle. There are 3 cases that can happen when we compute the middle. The target could be equal to the element at the middle. In other words, we found it, lo and behold. So we return that, and that's it. If this isn't the case, then we're not returning and we end up here. And so here we check to see if the lower one is equal to the upper one. That means there's only one there that there is. It's the index. That seems like if the upper is equal to the lower, then the target, the index, is going to equal to that. And so I don't see why this, how this is going to be any different than this. But if lower is equal to upper, return lower. Well, anyway, okay, if lower is equal to upper, and the target is not equal to that, then I think I'm not sure I'm not even sure we need this part. But in any case, if lower is equal to upper and the target is not equal to it, then we know that it's not in there. So then we can return -1. If the target is not equal to the index, and there's still room between the upper and the lower, then we are going to figure out if we're going to continue the search in the lower half, the part that's less than index, or are we going to continue search in the upper half, the part that's this half that's higher than index. And so if the number at the index is less than the target, if the number at the index is less than the target that we're looking for, then then the target must be in the upper half, must be higher, at a higher index than the one we're at. So we're going to search the upper half, and this is how you figure out the upper half. You just take the index and add 1 to it, because it wasn't that one. So we index, add 1 to it, and then the upper half stays the upper coming in stays the same. Otherwise, if this is if we reach this point, then it's going to be because num of index was greater than target. It can't be equal, because that would have been caught here. And in that case, we search the lower half. All right, so I still need to figure out the levels of recursion and the number of comparisons. Gee, that's an interesting question. Well, first of all, I'm going to run this to see if this part works. I'm going to have to say, let's see, can I count recursions? I think I can count recursions. I'm going to put right here recursions plus equal 1, because each time this thing is called, this calls it. Well, okay, that's what I'm going to put. So that'll have a value. All right, I'm going to see if that works. Then comparisons. Gosh. Really? Okay. Comparisons. 1. There's a comparison there. There's a comparison here. And there's a comparison here. So it may take 3 comparisons to get to this point or this point. All right, so those are the numbers. I'm going to see if this works. I guess I have to input oh, here's a nice list of numbers here. List of numbers, I'm going to say that. And then what number to search for, I'll say 2, just like that. And it says blah, blah, blah. Recursion referenced before assignment. Okay, I got to somehow tell it that it is a global. How do you do global variables in Python? Global variables Python. Oh, I know, I spelled it wrong. Spelled. Okay, it is in line 7 in binary search. Line 7 in binary search, yep, that's right here. And this is referenced for recursion comparisons. I'm gonna see what the solution is. You gotta say it's global. I wonder why it didn't tell me that. I wonder why this thing didn't tell me that. Oh, I didn't go down far enough? Stupid, I didn't go down far enough. All right. When you're reading documentation, read all the documentation before you start complaining that something wasn't there. So I'm supposed to say global. I obviously don't use global variables much in Python. I think every JavaScript, you got to do this. PHP, you got to do this. So I should have thought you'd have to do this. Recursion and global comparisons. All right. This means use the global one instead of defining your own. Okay. List of numbers. Let's search for 2. And I still got it. Did I use recursions again? Did I say recursions again? Recursion. Print. Oh, it's called recursions. That's the problem. That's why. Oh. One recursion, index of 1, recursions 2, comparisons 4. Okay, so comparisons 4. Why is comparisons 4? Oh, that's interesting because it works, but maybe I didn't need to do something. Let's see, what doesn't it think I need to do? Yeah, I don't need this. I don't need. Oh, there's no recursion. This should just be return -1. That was kind of silly that I had it in there. It would never happen. I wasn't counting it anyway as a comparison. Oh, 1 equals lower. All right, so here's how it works. Here's how they get their answer, okay? If target equals that, then return index. elif upper equals lower, then return 1. And for some reason, they say that this does not count as a comparison. I wonder why that doesn't count as a comparison. Oh, it says this does not count as a comparison because we aren't comparing a list element. And we're only talking about comparisons of list elements. This is comparing the indexes, the upper and lower bounds. Yeah, you could actually do that in here. You could do it at the very beginning and reject it and, you know, return -1 if, well, anyway, so that doesn't count. So that we're only, so a comparison here and a comparison here, I guess. So this is what it looks like this. So now if we do 1, 2, 3, 4, 5, 6, 7, 8, 9, looking for 2, it does show that. Anyway, okay, so I'm done with chapter 15. Did both of the lab exercises at the end, and so this should take you through chapter 15. We will start with chapter 16 tomorrow, I guess. Any questions?
What about assignment number 2?
Oh, you mean assignment 2? Let's see, what about it?
It's the same instructions as assignment 1.
Oh, really? Oh,
Yeah.
Did I not finish? I'm sorry. If that's the case, let me look. Oh, I didn't finish copying in the assignment. So sorry. I must have started this, like, I don't know, before break or something. All right, I will fix this, and I'll fix this by tomorrow. Okay, or when am I seeing you again? Is it tomorrow?
Yeah, tomorrow.
Can sit. Yes. Okay, very good. Yeah. So I guess I'll have assignment 2 and assignment 3. Oh yes, I remember where I was with that recursion assignment. Okay, good. Thanks for pointing that out. Yeah, I went in, you know, after break, I went in and I looked at, oh, I've got assignment 2 already. And then I just started thinking about assignment 3. I didn't realize that I hadn't finished yet. Okay, so I will do that. And okay, are there any other questions?
That's it for me.
Okay. All right. Well, thank you. And I will see you tomorrow and I'll have this finished. All right.
Okay, thank you.
Take care.
All right.